Hello.
Hello, good afternoon. Myself, I am Ashish. I am a research scholar at IIT Kanpur, and currently in my. I am just going to start my fifth year here at IIT Kanpur, and I am doing my research under Professor Priyank Ghosh and Professor Sudeep Kumar Mishra at IIT Kanpur in the geotechnical engineering specialization. I welcome you all to today's live interactive session. And what we are going to do is that every week video lectures are going to be released in the NPTEL platform by the NPTEL team. Those are recorded by Professor what we are going to do is that we are every week we are just going to revise whatever is being taught in those classes, and we will try to solve some problems regarding those topics. So the lectures are actually divided into 12 weeks. So we will be having, so similarly, so parallel to that, we will be having 12 weeks of these live interactive sessions, and also one more week on the 13th week we will be having a 1 hour long uh, sum up or summary session, so that it will be helpful for those who are preparing, those who will be actually giving the exam for this course. uh, so all the weeks on Sunday we'll be having this interactive session from 3 o'clock to 5 o'clock, and also these recordings will also be uploaded in the YouTube. We will be getting the link for those as well. And apart from that, whatever problems we solve and whatever work we do here, like whatever work I do here on this presentation, those PDFs also I will upload. Those also we will get the links of those also, and you will be able to access those at any time. All right. So every Sunday we'll be having this from 3 o'clock to 5 o'clock in the afternoon, just in August for 2 weeks there might be some changes in the schedule because I will be actually traveling uh, outside abroad. So there will be some changes in the schedule, so those I will let you know in the due course of time. For now we will be having it regular on Sundays from 3 to 5. And if you miss any session, you can always watch the videos or watch these recordings again in YouTube. All Everything will be recorded and uploaded there. So during the session, so we'll be keeping this very informal, and if you have any doubts or any queries or anything, if you can discuss, with the floor will always be open for discussion. And yeah, and this is just this is not very formal thing. This is, we will be keeping it very informal. Some problems we will be solving, some basic problems, so that we can revise our concepts, and just the basic things will be seen. So I am also not very proficient in this topic, like, because as I'm not working in this field. But even though that is the case, I will try my best to solve your doubts and like solve the problems for you. So the in the initial some weeks, this week and the next week, I think most of the theoretical topics are only covered. Like most of it is based upon basic, like, theory. No problematic concepts are actually solved, right? There are no problems to be solved. So mostly these cover main theoretical concepts. the basic theoretical concept like types of geosynthetics, then uh, what are the polymers that form the geosynthetics. So this was the topic for this, so there is no problem that we can solve. So what we will do in today's session, in the beginning, for the half of the session, what we will try to do, we will just try to solve some basic problems from the basic soil mechanics course, right, the basic soil mechanics, so that we can just recapitulate whatever we know from the basic soil mechanics, because these concepts are also, we will see in the later stages that these basic concepts are also actually required for us to solve some problems in this course, right. So just to begin, just as an icebreaker, what we are going to do is that today we are going to in the first half, today we are going to solve some basic problems from basic soil mechanics. So those were those things, that thing we are going to do. And I suggest that you also keep a pen and paper with you, and also you can keep your calculators with you, so that you can just along the course you can also just solve it, right. So it's better also keep on solving, so that we can have a discussion while we solve, rather than just I solving it alone. It will be better that you can also solve it yourself. So I will be asking you what results you are getting, so that I can match the answers with you, right. So I suggest that you keep your calculator and your pen, paper, and uh, everything with you, so that you can also engage with the with this problem solving session. So to begin with, this is a short introduction. I'm a PhD student at IIT Kanpur, as I mentioned. My hometown is in Assam, in Silchar, and I just completed my BTech a few years back. So I am not that old, as you can see, in 2020 from NIT Silchar, and then thereafter directly I joined the PhD program at IIT Kanpur in 2020 itself. And then I got selected as a lateral entry fellow in the PMRF program in 2022. And since then, since 2022, I am a PMRF fellow, and also I have I have been regularly taking such interactive sessions. In the previous semester also, I had taken a similar interactive session on geology and soil mechanics course, that is also offered in the NPTEL platform by Professor Priyank Ghosh. And in the last year also, this course I was there as a PMRF team. Apart from that, I love traveling and playing drums, and this is my website. You can just visit the website if you want to see anything more about me. And also, this is my email. And if you have any queries or any doubt, you can write to me anytime, even after the course ends. Anytime, if you have any queries or if you want to know anything, you can just write to me in my email, which is this ashish20 at itk.ac.in, and I will be happy to answer your queries. And also I have shared my LinkedIn link here. All right. So let's begin by solving some some basic problems from uh, our basic soil mechanics. All right. So we will be solving some basic problems from basic soil mechanics. So let us see some problems. Yeah. So let us read the problem first. Compute the shearing strength of a soil along a horizontal plane at a depth of 5 meters in a deposit of sand having the following properties. So we have a horizontal plane, and below the horizontal plane at a depth of 5 meter, what we are going to do is that we are going to compute the shearing strength of the soil, right? The properties of the soil are given, angle of internal friction is given, the dry unit weight of the soil is given, the specific gravity of the soil is given, the also you can see the water table, the depth of water table is given. So 2.4 meter from the ground level we have the water table. Also determine the change in shear strength if the water table rises up to the ground level. Okay, so two cases we are to solve. First case is that the water table is at 2 meter depth from the ground level, and the second case is that when the water table is at the ground level. So these two cases we are to solve, right? So we just so this is the ground level, right? So our water table is somewhat here for the first case at 2.4 meters. Okay, so this is the water table and this is our ground level. And what we have to calculate, we have to calculate the shear strength at a depth of 5 meters. Okay, this is at the depth of 5 meters. So what is the basic equation for calculation of shear strength? If you can remember, if you can recall, what is the basic equation which relates the shear strength to the parameters that are given here? If you can recall, what was that, what is the basic equation just relates the shear strength tau to the other parameters? What is that? If you can recall, what is that uh, equation, the basic equation which we get from the mode Coulomb criteria? Yeah, what is that? C plus yeah, C plus sigma tan phi, right? So C is the equation, sigma is our what normal stress, and phi is the angle of internal friction. So this is a sandy soil, so it's given that the deposit of sand. So deposit of sand, what we can do, we can assume that our C is 0, so 0 plus sigma tan phi. So C is 0, so our is nothing but tan phi. Now what we need to find, we need to find this is the stress. For that, what we need, at least we need to find the normal effective stress at that level, right? The normal effective stress at this level, at this level we need to find the normal effective stress or the vertical effective stress. So for that, first what we are going to do, so let us just write. So what will be that? Sigma is equal to what? 2.4. So this is 2.4, 2.4 into the uh, density of this part. So here the soil is what? We can assume that here the soil is actually dry. So we can write a dry unit weight, right? A dry unit weight is given. So this is 2.4, 2.4 times 17.06. So 2.4 times 17.06 plus this 2.4 minus 5, that is 2.6 times what? Times the submerged unit weight, isn't it? So here we will have to use the submerged unit weight. So for that we need to find out the submerged unit weight. So how can we do that? So the submerged unit weight is given by G minus 1 by 1 plus C into gamma W. So G we know, but this E, that is the void ratio, we don't know. So how to calculate that? That we can calculate from the dry unit weight. So dry unit weight is G gamma W 1 plus E, right? This much only. G gamma W into 1 plus C. So this gamma W, gamma D is given as how much? 17.06. G I have already 2.69. Gamma W is 9.81. So 1 plus E. From here what I can do, I can find out E. So please calculate the E value from here. If you can, if you have calculator, you can calculate. Please try to calculate the E value, is the void ratio value.
0.55.
Yeah, so it's 0.55, correct. It is 0.55. So now what we can do, you can put this 0.55 here. So this is what, this is 9.81. So this one, this submerged unit weight is going to come as 10.73 C per meter. So now what we can do, we can find out easily. So this will come out as 68.82 kPa. So finally we have the shear strength as 68.82 times 10, what is 5? 38 degrees, which will finally come out as 53.76 per. Alright, now Now the next task is, what if the water table rises to the ground surface? Then what do you think what is going to happen? The shear strength, the effective stress is going to increase or effective stress is going to decrease? What is going to happen if the water table rises to the ground surface?
Will decrease.
Yeah, effective stress is going to decrease. So just find out the new effective stress. It is nothing going to, it is going to be 5 times 10.73, because everything is submerged now. Is 53.62, right? So then again you can find out the shear strength from here. 53.62, 1038. So we will get some lesser value of this shear strength, right? So quite easy and simple. So with this we recall our basic concept of the shear strength, right? Now let us see one more problem, similar problem related to shear strength itself. A standard specimen of cohesionless sand was tested in a triaxial compression test, and the sample failed at a deviator stress of 482 kPa when the cell pressure was 100 kPa under drained condition. Okay, the condition is drained, means the pore water pressure is 0 here. Find the effective angle of shearing resistance of sand. This is the first part. Then what would be the deviator stress and the major principal stress at failure for another identical specimen of sand if tested under a cell pressure of 200 kPa. So let us forget about that. Let us solve for the first part now. So it is given that the deviator stress at failure is, right, and the cell pressure, what is the confining pressure? Confining pressure is 100 kPa. And what is this confining pressure? Confining pressure is nothing but the minor principal stress, right? The sigma 3. So this we can write as sigma 3 dash. So here it is dash. This dash actually refers to effective. Since the soil is in drained condition, we are saying that the pore water pressure is 0. So total minus 0 is will give us this is only going to give us the effective value, right? So this is the cell pressure. This is 100 kP. This is the cell pressure. The cell pressure is nothing but the minor principal stress sigma 3. Now what will be the major principal stress sigma 1 dash? What is going to be that major principal stress?
482 plus 100.
Yeah, 482 plus 100, that is a 582. Okay, correct. Now the first part is find the effective angle of shearing resistance of sand. So can you recall what was the equation that relates the uh, principal? This also comes from this 4-coulomb failure theory only. What is the equation that relates our principal stresses to the cohesion and the friction angle? Can you recall that equation? What is the equation that relates this with phi and c? So one more basic equation that we have, sigma 1 prime is equal to sigma 3 prime 10 square 45 plus by 2 plus 2ic tan 45 plus pi by 2. Okay, so this is the same equation, more Coulomb equation only, just written in terms of the effective stresses. Alright, so sigma 1 I know 582, sigma 3 also I know 100, 10 square 45 plus 2, and this is obviously 0 because c is 0, so this one is also going to be 0. So uh, just try to calculate this 5 from here, effective friction angle 5 prime.
46.
Uh, I'm getting 44.97. Okay, let us write it as 45.
45.
45. So, yeah, so done. So now let us go to the next part. So what is the next part? What would be the deviator stress and the major principal stress at failure for another identical specimen of sand if it is tested under a cell pressure of 200 kPa. So now I got the phi value from here. So identical specimen of sand means the phi is going to be the same for that specimen also. Now what it is asked is this: I am to find the deviator stress at failure. So for that, so now my sigma 3 prime is what? Sigma 3 prime is 200, right? So again I can use the same equation. 45 plus 45 by 2. So please calculate this. Then finally what we will do from here, I can get the deviating stress at failure, right?
1166.
Okay, 1 1, how much? 1 1,
66 kPa.
116, okay, approximate, right? So now I have my sigma 1166, right? 1166.
66.
1166. So 1166 minus 200, think what 966, right? Huh? So this is my final deviating stress at failure for the second sample. Okay, so very simple. This one also was, this problem was also quite simple. Directly just basic concepts of what is deviating stress, what is which one is the minor principal stress, which one is going to be the major principal. Those concepts we use just to solve the problem, right? Now let us see this next problem. Two identical soil specimens were tested in a triaxial apparatus. The first specimen failed at a deviatoric stress of 770 kPa when the cell pressure was 200 kPa. Second specimen failed at a deviatoric stress of 1370 kPa under the cell pressure of 400. Okay, so two samples are given, so four values are given. Right. Determine the value of C and phi analytically. Okay, so let us first do that. So two equations we will get with two unknowns, so we can easily calculate the cohesion and friction angle value, right? So say similar to the exactly similar to the previous problem, we can solve this one also. So what are the values of the deviating stress at failure? 770 and 1370, right? So these are the two values. And what is the cell pressure? Cell pressure is 200 and 400. So from here I can get sigma 1 for both, sigma 770 plus 200, that will be the my first sigma 1, and the second one is going to be 1370 plus 400, right? So now again we will be using the same equation. Right. So first one is 770 plus 200 is equal to 200. This is my first equation, and similarly second equation will be right. So now what we can do, we can also, if you want, you can do that now, or I will just write the answers directly, so no need to waste time in this actually. So pretty straightforward and similar to the previous problem. So just we need to analytically solve these two equations to get C and phi. So on solving, we get phi is equal to 36.87 degrees and 5. All right. Now the final part of the question is, if the same soil is tested in a triaxial direct shear in a, sorry, not triaxial, in a direct shear apparatus with a normal stress of 600 kPa, estimate the shear stress at failure. So please do this one. The same soil is tested in a direct shear apparatus. So normal stress is given C and phi, we already know from here, and normal stress is given as how much, as 600 kPa. So easily we can calculate the shear stress at failure, right? So please calculate this. So I have C, I have phi, and I also have the normal stress 600 kPa. So similar to the first problem, just the basic this equation, our basic Moore Coulomb failure theory we have to use. Okay, so this is the final result. All right, so quite simple and straightforward. Now let us see this. So this is the case of a CD triaxial, so that is consolidated drain triaxial test. So if you remember, in the triaxial test we have two stages. So the first stage is what? The first stage is our consolidation stage, and the second stage is the shearing stage. So consolidated drain means in the first stage we are allowing the consolidation of the soil sample to happen, right? Complete so and then after complete consolidation, what we do, we keep the drainage valve open and then we shear the sample. Okay, we apply the deviatrix test and we shear the sample. So as we are allowing drainage, this is consolidated drained test. And CD test actually generally take, as you might be knowing, that CD test actually take a long time to perform, because the shearing has to be very slow, so that excess pore water pressure actually do not develop, and the shearing is to be slow so that the water drainage is actually appropriate, right? So excess pore water pressure should not develop in that time. So loading rate should be adjusted in such a way that the water gets drained out without inducing any excess pore water pressure. So it's actually very slow test. Okay. So a CD test, what is the question? A CD test was conducted on a normally consolidated clay, yielding the following data. Minor principal stress is given, that is sigma 3 is given, and deviatrix stress is given. So similar problem only, we need to find the angle of internal friction, angle which the failure, the first part, the first angle of internal friction easily we can determine, right? From what the basic equation, whatever you use, from that you can easily determine the phi. Next is angle which the failure plane makes with the major principal plane. Okay, so this one is also quite easy. So please try to recall what was that. So if we know the friction angle, what is the angle that the failure plane makes with the major principal plane? That also please try to recall what was that. Okay, so say, sorry, yeah. So say uh, sorry, just a second. What's wrong? Wait, just a second. Yeah, so say, yeah, so say this is the sigma 1 and this is the sigma 2. So this is a section. Okay, and say the failure is happening along this plane. Okay, this is the failure plane, and so this is our this and this plane is our actually the major principal plane, and this failure plane actually makes an angle theta with the major principal plane. So that angle we are actually asked to find out. And third is normal stress on the plane of the maximum shear stress. Okay, so if you recall, the plane of the maximum shear stress and the failure plane, those are not actually equal. The failure does not occur at the plane of the maximum shear stress, right? So maximum shear stress is always occurring at an angle at a plane 45-degree inclined to the major principal axis, major principal plane. But the failure plane is that is not the failure plane. The failure plane is somewhat different, right? So that normal stress on the plane of maximum failure plane, where maximum shear stress, we are asked to find out. Okay, so we will see that. So first, let us find out the angle of ideal friction. So sigma 3 we have, sigma d we have, right? So what is sigma 1? Sigma 1 is nothing but 250 plus 275, which is nothing but 525 kPa. Now sigma 1 is sigma 3. Now phi I can, so what is the C? Can you tell me what is the cohesion value for a normally consolidated clay?
Zero.
Yeah, for a NC clay, for normally consolidated clay, it's always zero. Though it is a clay, so from here we can recall one more concept that we had learned in the basic soil mechanics, that this cohesion actually is not an inherent property of the soil. This cohesion actually depends. Okay, depends on the uh, what to say, the state of the soil. Say here the soil is normally consolidated, that's why we are getting CS0. So this cohesion is not the actual inherent property of the clay. The inherent cohesion which we actually get from the what to say, from the this electrochemical property, that is the cohesion between the particles in the clay, that is actually in practicality that is actually lost. That cohesion actually hardly plays any role. But this cohesion, this cohesion value, what we define here, this cohesion actually comes from something else. So if later if you study the concept, the some if you study some concepts called critical state mechanics, so in critical state mechanics actually we'll see that this cohesion is from where this cohesion actually comes from the metric suction. Okay, in over consolidated clays it comes from the metric suction. In normally consolidated clay, this that metric suction is actually absent, so that's why we do not get this cohesion. Okay, so that's why you get the cohesion is zero in that case. All right, so for normally consolidated clay we can have C is equal to 0. Now it is sigma 3 250. Okay, so from here I can get the phi. I will just give you the value 20.78. Okay, so we get the phi. The next is what is the failure, what is the angle that the failure plane. So this theta angle, what will be that? So can you recall what this theta angle is actually? How can we find that this theta angle, this angle theta, can you remember? So this theta is nothing but 45 degree plus pi by 2. So 45 plus is 55.35. Okay, done. The final thing that is asked is normal stress on the plane of maximum shear stress. So let me just draw a more circle. So this is the shear stress, this is the normal stress. So this is the point of maximum what to say, maximum shear strain, right? So here we have the tau max, right? Here we have the tau max. So this angle is how much? 45 degree. So what we are asked to find out this. Okay, this. What is the normal stress at this plane? Okay. So for that, what we have, we can directly use this relation sigma 1 plus sigma 3 by 2 plus sigma 1
Sigma 1
minus
minus sigma 3
sigma 3 by 2
by 2 into cos 2 theta.
cos 2 theta. So what is the sigma 1? Sigma 1 plus sigma. So sigma 1 is how much? 525 plus 525 plus how much? 250 by 2. And sigma 1 minus sigma 3 is nothing but our derivative stress. What is the derivative stress? 275 cos 2. So from here I will get 338.62. Done. Done. Now if I ask you what is the shear stress at the failure plane? What is
Sigma
that?
1 minus sigma 3 by 2 into sin 2 theta.
Yeah. So this was the normal stress on the plane of maximum shear stress. Now it is sigma tau is equal to sigma 1 minus sigma 3 by 2 times, right? So this will come out as 128.54. Okay, this is shear stress at failure plane. And one more thing, the last question, what is tau max? The maximum shear stress? This is the normal stress at failure plane. This is the normal stress at failure. Yeah, and this is the shear stress failure plane. Now I am asking what is the maximum shear stress? Very simple. This
The beta stress by 2.
yeah, correct. The beta stress by 2. It is sigma 1 minus sigma 3 by 2. How much is the elevator stress? 275, right? 275 by right. Okay, and wow, okay, so we found out the normal stress at failure plane, right? And what is the normal this normal stress that I was asking at the beginning? What is the normal stress at the plane of maximum shear stress? So this is the normal stress at the failure plane. What is the normal stress at this plane where the shear stress is maximum? What is this? That's simple. The distance of the center of the Mohr circle from here.
Can you repeat the question?
I asked that. See, what is this sigma and what is this that we found out? What is this one?
Normal stress on
At
failure.
at the fair, correct. And this is the shear stress at the failure plane,
Hmm.
right? And this is our maximum shear stress.
Right.
So at the plane where we are getting this maximum shear stress, at that plane what is the normal stress? That I am asking. At the plane of tau max, what is the normal stress?
Sigma 1 plus sigma 3 by
Yeah,
2.
sigma uh, sigma 1 plus, you are saying this.
Sigma 3 by 2.
Yeah, so this distance, right? The distance of the center of the mode circle
Exactly.
from the origin. Yeah, sigma 1 plus sigma 3 by 2. Right, so from here to here, it is sigma 3, right? And plus this one, so this distance is how much? Sigma 1 minus sigma 3 by 2. So finally you are getting sigma 1 plus sigma 3 by 2. Okay, so this is nothing but sigma 1 plus sigma 3 by 2, right? So if you want to calculate this, 525 plus 250 by 2. And so now let us see what was this is for the CU. So you saw CD test. So this is for CU test. So result obtained from a series of CU tests on a soil gave the following. So C is the equation is 0, phi is 17 degrees, and effective value of phi is 34 degrees. Okay, so total value of phi is 17 degrees and effective value is 34 degrees. Okay, if if the sample of the soil was tested in a CU test under a cell pressure of 180 kPa, determine the deviatory stress at failure, pore water pressure at failure, major principal effective stress at failure, minor principal. Okay. So CU test means consolidated undrained test. So in the sharing stage, the drainage valve is closed. So obviously while we are sharing, the sample is saturated, right? So water is there in the pores. So when we will share the sample, at that time excess pore water pressure is going to get developed. So we are asked here to find out the first we are asked to find out the deviatrix stress at failure. So let us find that out first. So number one, so sigma 1, so basic same thing we are going to use again. So sigma 1 is what? Sigma 3 10 square 45 plus 5 by 2, right? So what is sigma 1? We don't know, we can find out, right? So sigma 3 we know. Sigma 3 is 180 10 square 45 plus 5 by 2. So what is 5? 17. So this one will come out as 328.74 kPa. Remember, this is total stress, right? Sigma 1, not effective principal stress, major principal stress. This is a total uh, principal stress, sigma 1. Now second step is we are asked for, okay, so we are asked deviatory stress, so sigma 1 minus sigma 3. So let us just write it. 328.74 minus 180 148.74. Okay, so we get the deviatory stress at failure, this one. Now next is pore water pressure at failure. Now in terms of effective values, if I want to write down, I can write it like that. right, in terms of effective values. So now what is sigma 1 prime? Sigma 1 minus pore water pressure, let it be u. Okay, then sigma 3 minus u 10 square 40 plus 5 prime is given as 34 degrees like true. So sigma 1 I know 328.74 minus u 180 minus u. Correct. So we got this from, so if we just solve this ui can get us, so this is the pore water pressure at failure, right? So now what is the major principal effective stress at failure?
Sigma 1 minus U.
And minor also.
Sigma 1 minus U.
Yeah, yes, correct. 328.74 minus u, this one. So this is 207.37 and this one is going to be 58.63. Okay, done. So this was all from the basic this shear strength topic, which is like important to us every time. We need these concepts every time. Okay, in whatever subjects of soil mechanics we study, we actually need these concepts. And one more thing we are going to solve, two more problems we are going to solve now. Those two problems will be from the retaining wall thing. So retaining wall also we'll see in this course that we will be needing, it will be required to calculate the earth pressure and all those things, because we will be solving the problems where we will be designing this reinforced earth walls and all those things. So there we will be needing those concepts. So let us just solve some basic two problems from the retaining wall topic. Okay, let us see this. A retaining wall 10-meter high retain a cohesionless soil with an angle of internal friction 35 degrees. The surface is level with the top of the wall. Uh, the unit weight of the top 3 meter of the fill is 1.6 ton per meter cube, and the rest 2 meter rest is 2 ton per meter. We are to find out the point of application of the resultant active thrust. Okay, so we have some retaining wall. We have some retaining wall, and the retaining wall is actually 10 meters high. 10 meters high. The surface is level with the top. This is the surface is plane. The the unit weight of the top 3 meters is 1.6 ton per meter cube, and the rest 6 meter, that is we are having a 2 ton per meter. We have to find the application resultant active thrust. Okay, the active thrust resultant active thrust we need to find out. Do you recall what is the active earth pressure coefficient? How to calculate the active earth pressure coefficient?
1 minus sin phi by 1 plus sin phi.
1 minus sine phi by plus. So what is the angle? 35 degrees. So 1 minus sine 35 by sine 35 is going to be 0.271. Right? Very simple. So now what we are going to do first, so for the so it is 10 meter, right? So this is the 3 meter, say 7 meter, this is the 7 meters. Okay, so the first top portion, top 3 meters, it will be something like this, right? The variation of the active thrust, and what is this value? Ka into 3 into 16. 16 means 10 per meter cube. In kilonewton per meter cube, it can be approximated as 16 kilonewton per meter cube. So 3 into 16, right? And below that, this slope is going to change, and this one will be actually how much? This one is how much? This length, k times 3 into 16 plus 7 into 20, right? This is why this is this whole length, this thing, right? So this one, what we will do, we can actually divide it. Okay, we can divide it as, say, this one, this area you can calculate as 1, say P1, and then the below part we can calculate as P2. Okay, P1 and P2, and the total. And also what we can do, we can separate this one also. So let's say this one is P2 and this one is a P3. So the total P, active earth pressure, will be a sum of this P1 total, P1 plus P2 plus P3. All right, so now let us find out P1 plus P1 is the area of this small triangle. Okay, this is the area of the upper small triangle. So what is that going to be? Half into 0.271 into 3 into 16 into the height, is 3. So this one will be P1, right? Now P2, what, and if you want to calculate this trapezium, you can calculate this trapezium also. If you calculate the area of this whole trapezium, you will directly get one whole area. That also you can do. Okay, so that one also you can do. So it is up to you. Okay, so let me just write it like that. P is equal to half into 3 to 13 plus 7 into 13 plus half into 37.98 into 7. Okay, so this is what? This is this P1, this is P1, this is actually P3. P3 is nothing but the area of this rectangle, and then finally we have the P2. P2 is nothing but the area of this triangle. Okay, so if we do this, we will get 10 per meter. Done. So now finally what we need to do is that we need to find out the this uh, what to say, the point of application of this active thrust. Okay, so some height y below the ground level where this active thrust is acting, that we need to find out. That easily you can do again. So this one is how much? This one is 19.5, this one is 91, and this one is 132.93. Okay, so 19.5 into the distance of the centroid of this triangle from the bottom, from here to here. So 3 by 3, 1, 7 plus 1, it will be 8. 8 plus 91 into 7 by 2, that is 3.5, plus 132.93 into 7 by 3 divided by 243.3. If we do, we will get the y value. So this y comes out as 3.22 meters. So this is So this PA acts at a height of 3.22 meter from the, this is the point of action of this PA. All right. Right. So quite easy only, right? So just we need to divide. We can we if I draw this triangle here, whole figure here. So what we are doing is that we are dividing it into three parts. So this, for this triangle I know this height, I know this this base length. For this rectangle, this base length and this is going to be the same, and this height also I know, so I know this area, I know this area. Similarly for the lower triangle, I know the total length, so I can minus this one to get this length, and again I know this height also, so that also I can find out. So then I can find out this area also. So like this you need to do. Okay, so you can do this again by yourself and just check the results one. I'm not wasting any more time in this. And similarly what we are going to do is that we will solve one more similar problem. Okay, so this is a retaining wall, 5-meter retaining wall retains a cohesionless soil with an angle of internal friction 35 degree. The surface is the same surface, and the water table is below the bottom of the wall, means no action of water table, so no problem regarding that. Determine the percentage change in the active thrust if the water table rises on the ground. So two cases: once the water table is below the wall level, and one and the second case it is at the top. So in the two cases we are going to find out the active thrust. So say this is the wall. Okay, this is the 5-meter height wall. So for the first case, directly I can find out PA, right? So what is PA? Half. So the variation will be something like this, right? Right. So what is this? This is K times gamma. What is gamma? What is gamma? 17. Where is that? Yeah, that I forgot to actually give. Uh, this gamma is given as 17 kilonewton per meter. This is given. Okay. So half into 5 into 17 into Ka. So Ka is same 35 degrees. So previously whatever Ka we used 0.271 will be that only. Okay, into 5. So this is going to give us the PA in the first case when there is no action of water. So water is below the this uh, base of the bottom of the our retaining wall. So no problem regarding that. Okay. So this one if you calculate you will get 57.58 kilonewton per. Now for the second case our water table is actually here. Okay. For that case what we will do, first we will calculate the submerged unit weight. Is 20 minus saturated is given as 20, as 9.81 if we do. Now, so now there will be two parts, right? One triangle will be this thrust that is coming from the submerged soil, right? So what is this? So this is 5 meters. And what is this length? Can you say what is this? 0.271 into 5 into how much? 0.271 into 5 into 17, right? So this is the active thrust that is coming from the submerged soil. Addition to that, we need to consider the water thrust also. Water thrust also, right? So this is also 5. What is, how much will be this one? How much will be this one? 5 times 9.81, that is the unit weight of water, right? So this one is coming from the soil, and this one is the thrust from the lateral thrust that is coming from the water. Okay, these two here we have to add. So now our final PA will be half into 0.271 into 5 into 17 into 5.
Where from we got 0.271
271 is Ka.
K. Right.
But for water, this K won't be
No,
there. Right. And then we have half into 5 into 20 into 5. So now if you sum it up, okay. So now percentage increase, let us see. When the soil was, water table was below, what was the this one? Active earth pressure, it was only 58.57 kPa. But now when water is there, so when the soil is completely submerged in water, this is increased to 157.14. If you want to calculate the percentage increase, it comes at approximately 170. So you can see huge increase in the lateral thrust on the wall if the backfill soil is submerged, right? So always what we need to do, always we need to consider this in design, and always we want that water should drain out from the backfill as fast as possible, because if the backfill is submerged or there is huge amount of water retained in the backfill, that water is going to create huge amount of lateral pressure. Okay, due to these many retaining walls actually fail, if not designed, right? So always we need to factor this, take into account the proper drainage. Okay, proper drainage should always be, provision of proper drainage should be always be given in the retaining walls. So how can we provide drainage to the retaining wall, drainage in the retaining walls? One way, one
filter.
way is to directly provide weep holes, right? Weep holes. Other way is to use geosynthetic also. Along with weep holes, what we can do, we can use geosynthetic also. How can we use geosynthetic? So say
Geo board we can.
yeah, what
Geo board.
geo
Board.
geo geo board.
Geo board. This is sort of geo drain.
Yeah, correct, geonet, yeah, and yeah, exactly. So that we can use in the this interface between the wall and the soil, right? So that whatever water it is coming, the water can easily get inside this drain, and then it can drain out from the weep hole, isn't it? So say if we have a wall like this, say a cantilever retaining wall like this, and we have some drain here, right? So what we can do, you can provide some geocomposite, say you can provide a geonet like this, and then we can provide a uh, geo
Geotextile.
geotextile like this. Yes, correct. So what this geotextile is going to do, geotextile is going to work as a filter. It will prevent the soil particles to block this geonet, and the water will enter like that, it will flow through the geonet and just will exit out. So so it is very important that we consider this, else you can see that the lateral earth pressure actually increases more than so what to say, more than 2 times, right? So this thing we should actually consider. That's why I thought that we will just solve this basic simple problem. Okay,
In case of
so
cohesive soil,
yeah,
how to calculate the lateral earth pressure for retaining wall design?
for
Since soil
cohesive,
is fully cohesive soil.
yeah, for cohesive soil, if I can remember, we have, right, this if I can remember, Ka gamma z, this earth pressure is now this one, right? If Ka gamma z plus or minus, I forgot, plus 2ic root over Ka, like that we have the relation, right? Then the upper portion we have this
Negative.
for Ka it is minus, so yeah, negative, and then the below. So if you want, what we can do, uh, by intention actually I did not put that problem just to not to. What we can do in the next class, what I will do, we can solve one problem regarding that. Okay, many problems are were there in the last semester only. I had taught that course. I had taken this interactive session for geology and soil mechanics course. So there we solved a lot of problems regarding this for cohesive soils also. So what I will do is in the next class I will just in the beginning that we can just solve one problem regarding that. Okay, so that concept will also get cleared up. So that is also quite simple, only similar. It's very simple, similar to this. So now what we are doing, we are just using this, right? So but now this factor is going to also come out. And also one more thing we need to consider is that whether tension cracks have developed or not. So this there is a negative pressure that is acting at the top part, right? So there is that soil is in tension. So whether
Right.
it that place tension cracks are developing or not in so if tension cracks develop, that means that this part the soil that is it is not in contact with the wall, right? So only the bottom portion we have to consider. So now if tension cracks do not consider, what will going to happen is that this plus and this minus and this plus portion are going to get cancelled up to some extent, and the lower trapezium portion, this is going to only act. So what we're going to, we
The-
will solve, we can solve some these one or two cases of these problems we can solve in the next class, so that this actually gets brushed up, this
just
concept.
so, in case of cohesive soil, so shall we take Ka value?
Yes, yes, K only.
Then
Yes.
what should be
You,
the
oh, you are
phi?
saying 5, 1 minus sine 0 is 0, and 1 by c, 1 by
Then
1 it will be
K
1.
then K will be 1.
Yeah, 1 phi is 0.
Or we should take the effective phi in case of
uh,
design, returning
Acha,
wall design.
okay, you are saying t- telling about the phi value. Okay, that actually depends. Yeah, that is actually a little bit confusing. If you want to take
Yeah,
zero,
yeah.
yeah, that is actually a little bit confusing. It depends. Okay, effective five are taking. That means you are saying is that there is some pore water pressure that is undrained. The soil is in undrained state. That in that case,
Mhm.
effective five is going to come, right?
Actually,
I
no
just,
code is clear about this concept. What to do with cohesive soil in
okay,
retaining wall
yeah,
problems.
yeah, that
And
you are
in the industry, it's a lot more,
con-
I think,
con- confusing. Yeah.
confusion is there. And what people do, they simply take phi equal to 30 and do the design. But in
Uh,
most of the cases, it is over design.
yeah, yeah, correct, correct. Yes, yes, that
So
is a confusing thing. That
if
actually
you have
that.
any literature or any
Okay,
problems,
yeah, yeah, yeah. Whatever,
kindly,
yeah,
kindly.
yeah. I will see if I can find something on that. Yes, that one you are right. I will see that. The confusion regarding which fight to take, right? So
Which
whether
phi to take for?
see whether for it to take zero or some effective
Yeah,
value.
yeah.
If we take phi is equal to zero, then PA is going to be high, right? Higher. If phi is
Mhm.
zero,
Right.
yes. If K is one, then phi is this PA is going to be. Yeah, that we can see. I will just think. I can ask Professor also, Professor Rajagopal also. I will see if I can ask.
Okay.
Uh, okay, so let us just start. I'll see this now. So can okay. I hope you can identify this, right? Identify all this. So what is this first one? The first image. This one.
Geotextile,
Yeah, correct. So this is a
non-woven geotextile.
yeah, geotics. And what is this one?
Geogrid,
Geogrid, correct. What is this one here?
geocell.
Geocell. Then this one.
This is composite,
Yeah,
geocomposite.
this is a geocomposite, but it has a particular
PVD.
correct PVD. This is a PVD, and then this one,
Geonet, I think.
yeah, inside it is Geonet. This one, what we are talking about, right? So Geonet in the middle, and it is sandwiched between
Right.
textile, right?
Geotextile.
This is Geonet, and these are actually geotextile. And this one,
Actually, it's not clear actually. Oh, this is GCL.
correct. This is GCL, geosynthetic clay liner. So we
Right.
have here sandwiched between two uh, geomembrane and one geotextile. And what is this?
This is the liner, geomembrane,
Yeah, this is a liner. It's
pond
a
liner.
geomembrane, correct. Now, yeah. So I will. Yes. So this one actually we had gone for a site visit during my bachelor. So this you can see this PVD installation. So this crane. So what they were doing is that they were constructing a approach for a railway overbridge. Okay, means not road overbridge, ROB, and below it was there was a railway line. So they had to construct one road over ROB, and for the ROB for the approach construction, what they did was below the where the approach will actually come where above, so above this above this subgrade actually they were going to construct the approach. So before approach, what they did was they treated the soil with this PVD, they installed PVD so that they could actually accelerate the consolidation of the this subgrade layer. Okay, so after, so this one actually they could achieve, I think within 6 months, 6 or 8 months they could achieve almost say 80 to 90% consolidation they could achieve using these PVDs. Okay, and over that what they did, they actually constructed the approach of the ROB, and for the approach what they did, they used this reinforced geogrid. They use that for their approach construction. Okay, so now let us just so we have around 45 minutes left. So what we will do is that we will just revise a bit whatever was taught in the lecture session, so that anyone who sees this video again or it's just helpful for them, let us do that once. Just open the open whatever was taught. Yeah, yeah. So geosynthetic, as we discussed, geosynthetics can is natural or artificial. Natural or artificial. So natural, the most common is our jute geotextile. Jute geotextile that we use. Jute is the most common type of, so uh, jute is mainly used as a geotextile everywhere. So jute geotextiles are regularly used for this erosion control in slopes. So we put geotextiles there, and as it is very sustainable, what we can this green vegetation cover also grows over that, right? So it looks very nice, also looks very beautiful. So these jute geotextiles are very, jute and coir geotextiles are very common, natural geotextiles, jute, coir. And this artificial, so we know only these are made of what, polymers, right? Artificial are made of polymers, or you can have these strips, metallic strips, right? So metallic strips also actually are also used to uh, used as reinforcement. Okay, so if we get time we will solve some problems regarding the metallic strip also. All right, then yeah. Mm, yeah, so then comes the main functions, right? So what are the main functions for which we use geosynthetics. Right. What are the different functions for which geosynthetics can be used? So, can you tell me one by one what are the functions that we can recall?
Reinforcement,
Yeah. First is reinforcement. Yeah, reinforcement. Yeah, reinforcement. For example, some examples. If you can think of some examples where we use as reinforcement.
Ariwal,
Adivals, right? This is the most common example where we use what do you use for reinforcement? What kind of geosynthetic do you use for reinforcement?
geogrid,
Correct. Mostly 90% we use geogrid. So for this we use geogrid. So what are the types of geogrids that are available to us? Uniaxial and biaxial.
oh right,
Right. Yes, we have uniaxial geogrid and also biaxial geogrids. So geogrids are the main constituent whatever we use for reinforcement. Apart from that, geotextiles also sometimes we get, though you don't use that much, we can use geotextiles also you can use, and also these steel strips also we can use for reinforcement. Okay, then one more function.
filtration,
Correct. Filtration. For filtration, what do you use?
geotextile,
Yeah, we use geotextile. So what does geotextile? What is the purpose of filtration? The filtration purpose is that to allow water to pass through it, but to retain the soil particles.
right,
Right. So behind the RE wall, if you are using, so that time you are also using for the purpose of filtration only. You are preventing the backfill soil to go inside the drain and block the drain. Meanwhile, we are allowing water to pass through. So that is filtration. Then next,
next as the impermeable membrane,
yeah, that is what? That is barrier.
barrier,
Barrier,
right,
right? So barrier. So this what do you use for barrier?
geomembrane, GCL,
Yes, geomembrane and GCL. These are the two most common
barriers,
common barriers that we use, that are geomembranes and GCLs. So geomembranes are nothing but those, not the kind of that polythene or whatever sheet that we see. Similar to that, geomembranes are like that only. And the main, so some actually these there are some properties of this also that we need to also to consider while we use that. That also we'll see while we progress in the course. So that we also need to consider, because the strength of these geosynthetics are also important. So what strength of geosynthetics you are using in what condition, that depends on what condition you are going to keep that in. Okay, so for geomembrane, apart from this mechanical strength, this chemical, like the chemical resistance is also important, right? So because these geomembranes are actually used as barrier, so mainly industrial waste and all these are dumped in landfills, right? The specialized landfills or ponds that are made with geomembrane lined ponds that are made for dumping this industrial waste or something like that. For that case, we have to ensure that the chemical that we are dumping, that does not corrode the geomembrane very easily. Right, the geometry should last its design life. Right, else what will happen? Else that material will damage the geomembrane, and then that harmful substance will actually leach into the ground. Once if it leaches into the ground, it is going to then damage the ground surface. It is going to damage the groundwater table. The groundwater table is going to get contaminated. There are going to be a lot of things. Right. So these things are also very important that we need to consider. Okay, so then more functions.
drainage,
Yeah, drainage you can use geotextile, and what geonets you can use, right? Drainage. Then next,
erosion control,
yeah, erosion control. Erosion control you can use geotextiles. Geotextiles you can use for erosion controls. So in the slope you can put geotextile uh, it is always preferred to put this jute geotextile. So we have in India national jute board, right? National jute board is actually they are actually promoting this jute geotextile and coir geotextiles to a large extent nowadays. So they are investing a lot in this because this actually also gives employment to the small scale industries, right? Construction of these jute textiles, and it is sustainable also. Easily plants can grow over it, right? So that is very prevalent nowadays. Then next, erosion control done, then filtration done, barrier done, drainage done, reinforcement done. Then one more important thing is remaining.
Gabriel,
What? uh, Separator.
separate.
Separation, right? Separation, where does this function come into play, if you can recall? Where do you use this separation separator, and what do you use a separator?
Below railway ballast
Yeah, to separate the subgrade so that
to
the
separate to
yeah,
come out.
yeah, subgrade to enter into the ballast, right? So what do you generally use geotextile, right? Generally use
Correct.
geotextile. Yeah, so railway and one more also in road constructions,
Road construction of also.
separate the this gravel coats and the sub base. We use this separator, right? So in that case, you actually this separator actually performs more functions. So say this is the subgrade, right? Subgrade, and here we have this gravel layer, and here you are putting our geotextiles. So one thing it will perform here is it will perform as a separator, this geotextile. And one more thing it will do is that, say, when this load will be coming on top of this uh, geotextile, what is going to happen? It will just prevent, because it has some tensile strength, right? So it
Yes.
will prevent the expansion. The tensile strength is going to prevent the
Hmm.
expansion. So that is actually also going to give some strength to the road.
Strength also.
Yeah. So that is also the one effect. One effect, if I can recall, I get there is an effect called membrane effect. Okay, the one there is an effect called membrane. If you study the book, so are you follow? Have you like? Are you referring some book for this course?
No, kindly suggest.
Yeah, please read the books by Corner. Okay,
Corner.
Corner. I will share. Yeah, Robert M. Corner. Those are very good books. Okay, Robert M. Corner's book on geosynthetics. Those are the best books, I will say. Very simple and very good books. Robert M. I will just share the name. Designing with Geosynthetics by Robert M. Corner. These are very books, very good books. Actually, two volumes are there, volume 1 and volume 2. Designing with Geosynthetics by Robert M. Corner. So Corner is actually regarded as one of the stalwarts in this field of geosynthetics. Okay, he's the one of the main persons who is actually uh, main persons who actually developed this field. He is Robert M. Corner. He died, he passed away a few years back, not that much. I think in 2019 or 18 or 19 he passed away. But that he is like the legend of this field. Okay, so this for the basics, this book is like very good, and it can actually help you as a very good handbook. Okay, designing with geosynthetics by Robert M. Corner. These are two volumes are there. By Robert M. Corner. So these are so this book is actually very good, and we will be solving some problems from this book. And what I suggest is you can go through the theory, whatever is given. If you go through very in very simple language, everything is given. You can easily understand. Okay, whatever is written in that book. So I suggest that please read that book once. All this whatever I am saying, all these functions, everything is very simply and very beautifully written in that book. This membrane effect, separator, everything, whatever I am speaking, everything is given there. Okay, so I suggest that you read that book once. It's very good. Designing with Geosynthetics by R.M. Corner, Robert M. Corner.
Is it McGraw-Hill publication?
This is let me see, not McGraw Hill, I think. I have the book with me. Just show you. Latest one is the sixth edition. One thing I think. Uh, Publisher I don't know actually. Uh, 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 Libris, publisher is Libris, not McGraw-Hill. This book. Let me show you this one. These two volumes are there. Now sixth edition is actually two volumes, volume one and volume
Okay.
two. This book.
Okay. Thank
These
you.
are Geosynthetics. Okay. PDF, I think you can get somewhere in the internet. If you search, I think you will get.
That will be better. You get the PDF.
Yeah, yeah. I think you will get. If you can see in Libgen, I think you will get. You know
Okay.
Libgen, right?
Sorry.
Libgen is a website where you can. That is actually not an. This is a. What is it? Okay, I will. You just give me a email. Okay, I will give my number. You just WhatsApp me. I will give you the link.
Okay. Okay. Okay.
If I find, I will find it out to give you that. I will just give my number in here. Uh, just a second. Let me check. It's there. Yeah, I will just share the my number. Just message me once. I will send it to you.
78738. Then
The first edition, fifth edition is actually available. It doesn't matter. Most everything is.
can you share your number once again?
Yeah,
Seven
it is. Yeah.
78738.
787-387-2969.
78738 72969.
And 387-2969.
7296. Okay. Thank you.
Okay, so yeah, so what we are speaking about, yeah, functions, right? So let me just show you one thing now, then we can continue. Okay, so before that, let us just recall what are the types of uh, geosynthetics that we actually have. So first one is geotextile, right? Then we have geogrids, then we saw geonet, then we have geomembrane, PVD, GCL, right? Then geocomposite, geocell. Also, we have some more things called geobags, right? So, geotextile, it is woven or non-woven, right? So, woven means it is woven, right? Whatever textile we are wearing, these are also woven, right? So, like that, it is woven. And non-woven means the strands are actually somewhat haphazard. They are either heat bonded or needle punch. There are various manufacturing processes. Those actually make the non-woven. So various what to say, various functions. In various functions we need various types of geotextile. Woven, somewhere we use woven, somewhere we use non-woven. If you want if you want to have the if you want that the geotextile also has some say strength, show some reinforcement properties, then obviously we are going to use woven geotextile, because non-woven geotextile won't be having any strength in any particular direction, right? So non-woven is generally used for this filtration and other purposes, right? Then we have geogrids that I already said, uniaxial geogrid and biaxial geogrid. Uniaxial geogrid is having strength in only one direction. Biaxial geogrid is having strength in both the direction. That is also dependent on where we are going to use that. That is based on that we are going to decide what to use. Then geonet we already saw. Geonet has a predefined plane where the water can easily flow through it, so that is mostly used for drainage purposes. Geomembranes we saw, for barrier purposes geomembrane is used. PVD, what is PVD? PVD is used for what is PVD used for?
Drainage.
Drainage, to accelerate the consolidation. What does it do? It reduces the drainage path, and hence it actually accelerates the consolidation. So we know this at CVT equal to CR square into time factor, right? So this is the main equation of the consolidation equation. So if the drainage path is reduced, this time if this drainage path is reduced, this time required for consolidation to happen, that will also get reduced. So what happens? So say a soil, so say we have a clay layer like this, okay? Clay layer, in the bottom we have sand, we have a clay layer like this. And in the normal course of process, if we apply some load at the top, the water in this clay layer will drain only out in this direction, right? So this consolidation process is going to take a lot of time, and this time is, if you recall from the consolidation chapter, this time is actually dependent on what? Dependent on the coefficient of
Length of
consolidation.
drainage.
Yeah, dependent on the coefficient of consolidation, CV, and that CV is actually dependent on what? The porosity and all those properties. The permeability of the soil. What is the permeability of the soil? Right? If the soil is less permeable, it is going to take lot more time to drain out, for the water to drain out. Hence, the consolidation will take lot more time. So today, say I construct something over this soil. After 50 years, I will see that my building has tilted, something like that, or my road has. After 5 years, I will see my half of my road has actually subsided down. Why? Because of the consolidation settlements that are going to take place. So what we do, we install some vertical drains known as prefabricated vertical drain. So the prefabricated vertical drains, it has a core and it has a outer covering. The core has some grooves. The core is like some plastic material, okay, some polymer material. It has some grooves there, so water can actually flow through it, and it is covered by a geotextile. That geotextile, that covering of that core outside membrane, that covering actually acts as a filter layer. Doesn't allow the soil particles to get into that drain, right? So that whole thing actually forms the PVD. So what you do, the PVD actually, so now the water particles can easily enter like this into this drain, and then easily flow out at the top and the bottom. So drainage path, what you are doing, you are reducing the drainage path and you are giving more scope for the water to drain out. So in that way, what you are doing, you are reducing the time required for consolidation. Say for 90% consolidation, previously it would require 50 years. Now for 90% consolidation, only in 1 year will be sufficient. For in 1 year, 90% consolidation will be achieved. After that, after 1 year, what we can do? We can start our construction. Whatever we decided to construct, we can do that. Right? So this is how this PVD is beneficial. Then we have GCL, geosynthetic clay liner, that is also act as a membrane similar to geomembranes. Okay. Then we have geocells. Geocells are also more interesting thing. So what are geocells? Geocells, what they do? So geocells form a honeycomb structure, right? So honeycomb structure, and we fill the geocell with say aggregate or say a this cohesionless soil or something like that, so that the layer whatever we are making that gets strengthened up. So what will happen whenever load will come over that geocell, that load is going to, so whenever the load is coming on a geocell, load is coming, so it will try to expand, try to get expand, the geocells will try to get expand. In that way, what will happen, some passive, there is some passive action. Okay, inside the geocell there is some passive action, some passive forces developed, some passive forces developed, due to which it gives strength. Okay, so geocells can be used in many places. For in road construction it is used, it is also used for slope protection, it is also used in this in what to say, in layered uh, earth retaining layered earth wall constructions it is used. Then it can also be used in defense purposes. You will say, how in defense purposes? Say you want to our armed forces want to rapidly construct a barrier, say this trench, okay, for their protection. So easily just they can carry these geocells, they place layer by layer, put soil in that, and they can just easily form a wall, right? So this geocell has versatile uses, and it is like rapidly used nowadays since many years, last 10-15 years it is used rapidly in this construction. You might have seen in many places it is used, and mostly it is used for this in this pavement construction. So we'll see one example where this is used. Okay. Then we have geo bags and geo pipes. Geo bags are nothing but bags that are filled with some aggregate or some aggregate mostly, or some soil, and those bags are actually put in the banks of the river to prevent erosion. Geo pipes are also similar. So these are erosion control structures. Okay, erosion control structures, it prevents the river bank erosion. Okay, so some pictures, let us see some of these pictures or whatever. Okay, so I wanted to show you, okay, this, let us see this. Okay, uh, so Shankar sir, where are you from?
I'm working in Mekong Limited, Ranchi.
Okay, Rachi, you are from Rachi. Okay, so
I'm basically from Calcutta, but I work in Ranchi.
okay. So this one, this Strata, you might be knowing this company, right?
Yeah,
So
yeah,
this,
yeah, yeah.
yeah, this company, this that they, this is, it is very famous. So they actually, so this was the condition of the highway. The first picture that we see, that you can see here. So this was the actually the condition of the highway that connected Assam to Tripura. Okay, so the main highway that was previously, it was NH44. Now I think the name has changed. So previously it was NH44. Now the name has changed. So uh, the main highway that connects Tripura with Assam, and then from Assam it connects to Meghalaya and rest of the India. So this was the condition of the highway. So they used to construct the highway every year, and every year after the monsoon, this used to be the condition. This used to be the condition of the highway that used to become. It used to become like this. Okay, every year this problem used to happen, every year. So it is to create huge problem for the people living in that, in the state of Tripura. So this photo is from near the place called Churaibari. So Churaibari is the border between Assam and Tripura. Okay, so this picture is from there. So what they did was, they actually excavated this whole portion out. First what they did, this whatever muddy portion you see, the main you lot of amount of soil, what they did was they excavated, then they put this section. So first they made a subgrade, then two layers of uh, granular subbase they constructed using the geocells. Okay, so one, so over the, so this is the, so first they had the subgrade. Over the subgrade they put as this non-woven geotextile. So this geotextile, what purpose you can understand, right? So this geotextile serves as a separator here. Non-woven geotextile, it serves as a separator. So one non-woven geotextile they put, and over that what they did, they put two layers of these geocells filled with aggregates. Okay, granular aggregates they put, and they compacted. And after that they, above that, so they first built the main base of the road, base of the pavement with this granular surface, and then above that they build they constructed the so this bituminous course, DBM and granular base, these are the part of the main pavement, and below that they form the other, these three the three layers they formed with this subgrid, and the two layers with the this geocell, and above that they built up the pavement. Okay, so then what happened, this actually gave a very good, this showed very good performance. As you can see the road, this is the picture from the construction, and this photo is after one season. Okay, after one season of monsoon also, so you can see the road is very nicely, it is there. Okay, so this geocell actually prevented the, like, helped in solving this problem by a large extent. Without this geocell, this problem would have been like very difficult to solve. Okay, so this was the problem there. So this details is given here. So previously it was actually NH44. Now I think the name has changed, and the client was obviously this PWD NH, government of Assam, and this Tata actually they gave this solution. Okay, here, okay, so they have this one also there. Yeah, this one also I was speaking about this thing. This case, so see, with the geocell, what they did with the geocell, we can also actually construct walls, right? In layers you can put the geocell, and you can see beautiful vegetation cover has actually come up with that. Okay, and this is the RD wall construction. This we will solve this we will solve some problems at that time. We will see this. Okay, how we will see some videos also, how step by step this is constructed, this all these things we will see, and we will, while we solve the problems, while we solve the design problems for this. Okay. And this geobags I was talking about, you can see the geobags here that are actually used for this river bank protection. Okay, and see, so geobags, what, so the what happens is that if you place the geobags, even if, so the water actually, what happens, it the geobase actually prevents the inherent soil, the main virgin soil, whatever is there, it prevents that to come out with the water. So water is there in the flood, water rises, so when water level reduces, what happens, the water actually carries away a lot of the river bank with it, right? So what happens, this geobase actually prevent that. It prevents the main original soil to flow out with the river. So these geobags are also regularly used. So here also you can see non-woven PET PP geobags, polypropylene PET, polyethylene or polypropylene geobags. Okay, so one more thing is there. We can see this geo pipes also. Not this one. Not this. Not this. Geobags are something else. It is not shown here. I think Saret put some images. This is not geo pipe. Okay, so there are many examples wherein these geotextiles are regularly used, and we will see this one by one as we solve some. We will solve the design problems also. So the design problems, what we will solve in this interactive sessions will be quite simple only, very easy, and I won't be taking I won't be considering the this seismic part into action while I solve these problems. But whatever, so I will be solving some problems, and some problems, if you see
You
the
are not
lecture,
audible.
sir has also solved many problems in the class also. So in the exam or in whatever, when the questions will come, please consider the earthquake and other those forces. So we'll discuss that later, we'll see that later. So in this interactive session, a live session is actually difficult to, so we will solve easy basic problems only, but we will try to clear up the basic concepts, okay, regarding the design and everything. It will be clear. Okay, so this was all about the types of geosynthetics, and one more. Okay, so then what was discussed was the this, what to say, this your polymers, right? Polymers. So I saw the that the assignment. So sir, will you be giving exam also for this course?
Yeah,
Yeah, yeah. Okay, okay. You will be like you are like you will be getting the certificate also, right? For that.
yeah.
Yeah. So for that exam, for this, so for that actually these assignments and all are also important. And in the assignment I saw that there are some there are problems regarding these polymers and all also. So what I suggest is that you please go through this portion also. It is, I know it is very boring because it's very theoretical, and when I also studied this course during my bachelor's, it was also, this portion was very boring to us also. So but what to do, this is there, this is the part of the syllabus, so we need to cover that. And questions also might come in the final main exam also, and as you saw in the assignment also, questions are there. So these polymers and all these are also important. So you might be thinking that why is it actually important, why do you actually have to study the polymers, and what are the percentage of what chemicals actually are. So what happens is that whenever we take quotations from these companies, like say Startup Web or something, McAfee or whatever, whenever we take quotations from them, so they will send their brochure, and so we have to actually sometimes check that whether they are using this good quality this material or not, whether that whatever their polymer they are using it in appropriate percentage or whatever, that we need to check. That's why actually these things are also important. We should actually know what polymer is used to construct that kind of geotextile. So that's why this is also important to study. So yeah, so the main basic types of polymers are our, I will just write it here. These are the main types. So polyethylene, polypropylene, polyvinyl chloride, PVC very common. Then PET, ethylene terephthalate, PET, uh, polyamide, that is nylon 66, and polystyrene. These are the main six important polymers that actually form most of the geosynthetics. Alright, these are very, so polyethylene, these actually the geotextiles are formed, geomembranes, geogrids are also formed, geopipes are formed, geonets are formed, geocomposites are formed with this. Then we have polypropylene from geotextile, geomembrane, geogrid, geocomposite. Then we have PVC, as you can guess, geomembranes obviously, geocomposites, geopipes. PET, we have geotextile, geogrids. Then polyamide, geotextile, geogrids. Polystyrene is, so yeah, this one, geofoam. We forgot to discuss about geo. So geofoam is also one more important geotextile that is used nowadays. So geofoam is nothing but thermocol, like thermocol only, if you have seen. So geofoams are used regularly. You can use it for say, you can use geofoams for, what to say, your,
Behind the
behind the
retaining wall.
retaining, yeah, behind the retaining wall you can use it, reduces the earth pressure. You can use for embankment construction, lightweight material, easily fast you can construct small embankments. Then you can use it as vibration screening. So one of my colleagues here is doing research on that. He has done some experiments also. So geoforms are also a uh, very good material for vibration screening. So vibration screen, do you know vibration screening? What vibration screening is?
Vibration isolation. No,
Yeah, vibration isolation. You know, right? So vibration isolation for say railway track,
machine
you have,
foundation
yeah. So
or
you,
machine foundations. Hmm.
yeah, for machine foundation, active or passive isolation, whatever. So that case also these geoforms are actually very much useful. Geoform. And I won't let us not discuss the properties, those were already discussed in the class, the properties, the different testing methods and all those things. Let us not again discuss. Yeah, and one more thing, please go through the how these are manufactured. Okay, those are also actually important. We should know the basics, right? So how geotextile is manufactured, how this, what is the this weft direction, because these terms are actually used. What is the weft direction, what is the this other, what is the, what is this called, weft, and I forgot, I also forgot. So there are two directions, right? One direction in which the geotextile is woven, and the other direction is perpendicular to that. So those directions, the terminology is associated with those things. Then how non-woven geotextile are actually manufactured. Then how we actually manufacture geogrids. Geogrids, how they're, how uniaxial geogrids. So we punch and then we extrude them. How by extrusion, by there are many techniques. So those actually also you should go through once, right? So actually this helps, because whenever some manufacturer actually says us that we are using this technique, so that should actually strike in our mind, right? So I know, if we should know as engineers, we should know that this technique is this, so this is this theoretical is manufactured using this technique, and vice versa. So it helps us to visualize properly rather than using it like a black box. We should actually know whatever, what processes are involved in the manufacturing of it, right? So geogrid, how they are considered. So one is by stretching, then we have knitting also. Geogrids are considered by knitting also, all those processes, there are many processes. Okay, then uh, geocells, how they are constructed, how they are actually tied, all these things are actually we can uh, actually we should know. All right, so this was all. I think there is nothing more. uh, it's better that I don't discuss, means there is no use of discussing all this again and again, because in the class everything is discussed. And if you see this corner, in corner's book, everything is, all these processes, everything is given, also given.
Okay.
So I suggest that you should go through that once. Everything is given there very clearly and stepwise, and like very systematically everything is arranged. So it will actually help you a lot, and some design recommendations are also given. And apart from that, we will be regarding design in this interactive session, we will be solving some basic problems. We won't be referring to any codes or anything, but whatever sir is solving in the class, that you should solve properly, because in the exam, if some design comes, if you have to solve, I don't know how the questions are set. I think it is multiple choice only, but then also I am not sure how in exam how these questions actually comes. But design problems actually you should solve in, however, in whatever way sir actually solves, Professor Rajagopal actually solves in the class, because he also mentions the codal provisions, from which code, say Federal Highway Administration, that code from which everything. So everything, uh, class lectures, whatever is taught there, I suggested you follow that properly. And apart from that, just for practice, you will be also solving some basic problems, you also will be solving. Okay, then all your concepts will get cleared up. Okay, and in the while solving also we will be seeing some videos and all, so that will also be like pretty helpful to us. Okay, and in the meanwhile, if you have any like doubts and all, if I am able to answer, I will answer. Else, I will convey it to Professor Ajagwal. If he has, if he so because if he if he is able to, he will also respond to that. Okay, and regarding whatever you asked today for that five value, that one I will try to see if I can find. If not, I will ask professor regarding that.
Okay.
Yeah.
Okay. Okay.
And yeah, that's all. This polymers, just go through this. What are the different types of polymers? What are the functions, and what how the manufacturing process of geotextiles, geomembranes, geogrids. These are the three important manufacturing processes that you should know. Okay, then that we have discussed everything, and we solved some problems also, basic problems, so that we can recapitulate whatever was taught.
Where can I get a complete geosynthetics testing laboratory?
Geosynthetic testing laboratory. Uh,
Exclusively geotesting testing laboratory.
there are many IITs. I don't here. I don't think we have that. Means we have some, but IIT Hyderabad, I think they have. And IIT Madras, and in IIT Madras, Professor Rajagopal had a very extensive testing facility, geosynthetic testing facility.
Mm-hmm.
Can contact IIT Hyderabad, and in IIT in IIT Madras. I was seeing in IIT Hyderabad also they have some food geotesting facility, if I can. And if you want nearby near Rachi, I think you have ISM. About ISM, I don't know if they
No, they
have.
don't have. They don't
That
have.
yeah. Here we have some, but I am not sure. Better, and you can contact in my BTech, that is in NIT Silchar also we have this
Okay.
unit. Yeah, if you want, you can contact Professor uh, um Ashim Kanti De. You can contact him. He is the in charge. Like he deals with this very openly. And you can obviously you can contact Aja Gopal sir. He is like the one of the main persons in
Mm-hmm. Yeah.
this. So this so yeah, so Rajakpal sir has a very good had a very good lab in IT Madras, but now he got retired from IT Madras, but still he will be having these things. But you can contact in IT Madras. IT Roorkee, I don't know if they have or not. We have some, but not. I think now I don't think anyone is working extensively in that this thing.
What is your research area?
My research area is little bit different. My research area is in this. Soil dynamics and earthquake engineering, mostly earthquake engineering regarding.
You are not audible. You are not audible.
Yeah,
Hello.
yeah, hello.
Huh, huh.
Yeah. My research area is in geotechnical earthquake engineering and soil dynamics. So
Okay. Okay.
in earthquake engineering, I have my research is in this one in vibration control. So in
Okay.
vibration control, and then uh, earthquake engineering, I am also studying how different types of earthquake actually affect art structures like art dams. So we have art
Okay.
dams, right? So in art dams,
Mm-hmm.
how different types of earthquakes, how pulse characteristics of earthquakes are affecting the art dam. Those things I am actually studying, dealing. And what is
Okay.
the fluid? How the fluid? So art dam we have water, right? So water is retained by the dam. So if
Mm-hmm.
the water physically affects the dam, not the no, I am not speaking about the pore water pressure changes and all those. Not that. I am
The
speaking
wave. You.
yeah, exactly. The sloshing of the water, whether it is affecting the characteristics of the dam, all those things. Actually,
Okay. And seismic effect also.
yeah, seismic effect, earthquake, seismic. And one of my colleagues is actually he has done a lot of experiment in this vibration screening. Okay, my senior also did in vibration screening using bamboo, and one of my now my who is my friend, he is doing with geofoam.
Okay.
Is doing geoform. So these things are in our research group. All are doing in this dynamics only, mostly in soil dynamics or earthquake engineering only, mostly are doing. And some are doing with some this computational geomechanics. Like you might have heard uh, method of stress characteristics and all these things. There are some computational techniques like you might have heard limit analysis. You might have heard limit analysis, method of stress characteristics. So some are working in that field.
Okay.
So, so like that only.
And Dr. D.N. Singh is there, no?
Dr. DN Singh, no, in our department, Dr. DN
You are
Singh,
in IIT Mumbai.
no, no, DN Singh is in IT. I am in IT Kanpur.
Oh, you are in IIT Kanpur. Sorry,
Yes, yes,
sorry.
yes, yes, yes. Professor DN Singh is in IT
In
Bombay.
Mumbai, Mumbai.
Yeah, 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 yeah. Professor DN
So
Singh
your
is in.
research guide is
My research guide is Professor Priyank Ghosh and Professor Priyanko Ghosh and Professor Sudeep Kumar Mishra. So Professor Mishra is from structural engineering
structural.
background.
Yeah, yeah,
Yeah,
yeah.
yeah, yeah, yeah. And
His younger brother is working in our
okay, okay, okay,
company. His own brother.
okay. Sudeep sir. So Sudeep sir is from structural background and Priyanko sir
Structural,
is
right?
from geotechnical background. So sir,
He was dean sometimes.
you did your BTech from Bengal only?
Yeah, Shivpur. We
Shivpur,
take an MTech both from Shivpur.
Shivpur only.
Long back, long back. It is 35 years ago.
Okay, Sudeep sir is also BTech from BE College only, I think.
Yeah, yeah, yeah. He's
Yeah,
much
yeah,
junior to me.
yeah, yeah. So
I
you did
did
not,
my, I
you did,
graduated on 1990.
okay. You did not, you did not try for PhD.
No, some 10, 15 years back, I registered in
Art.
ISM Dhanbad
Okay,
under
okay.
Rajiv Sarkar,
Yeah, yeah, yeah. Different.
but I didn't start.
Okay, okay, okay. I think it's difficult little bit because
Yeah, yeah, yeah. Maintaining professional
with
life,
work is it yeah, it's very difficult.
very difficult.
And you're like you are working in that you might have changed company na yeah, or you are working there only from the beginning.
No, not from the beginning. But here I have been working for last 27 years.
Okay, okay, lot.
Yeah, yeah.
Lot.
Earlier I was in Larsen to Grow, some
Okay, okay,
geotechnical investigation companies,
okay,
to
okay.
grow.
This sir, your like sir, your company is which what
We
means what is your specialization?
no, we are basically consultancy organization for
Yeah,
industrial plants, basically
yeah.
for steel plants. We are part of SAIL, basically.
Okay, okay, okay.
Steel Authority of India.
Yeah,
Earlier it was SAIL only. Now we are
civil constructions only.
doing separately.
All kinds of
For
civil
all the steel plants, we are the consultant. It is a multidisciplinary company.
now we are IIT Kanpur is offering on MTech
Hello,
program.
you are not audible. You are not audible.
Hello, hello.
Huh, huh.
Yeah, I am saying the IIT Kanpur is offering some e-masters program also. If you want that one also, you can join in future. Uh,
E-masters.
yeah,
What is that?
e-masters you will get a master's degree from IIT Kanpur only, but that
Okay.
is e-masters means from there by like it is remote from
Mhm.
there only you can do classes are held online and some evaluation everything quizzes everything are held online only, and it is flexible like you can say one semester you do now, one semester you can do next next term also, or 1 year later also you can do. It is very flexible.
Okay, okay, okay.
Okay, so that also you can see once e-masters you can do because many that is for industry professionals only.
Okay.
Okay, so that one you can see one. So we'll get and then once then campus visits also organized for that. So
Acha. Huh.
yeah, yeah, yeah.
I've got
E-masters.
it.
Yeah, yeah, yeah. Masters you can see.
One Mr. I forgot his name. He was in IIT Kanpur for a long time. He was basically expert in fly ash. Forgot his name.
Patra, NR Patra sir.
No, 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 no.
Patra sir, he doesn't fly.
Anyway, I'll tell
Okay,
you.
okay. Okay, okay, sir. Then we will end today's session. We will meet next week, and yeah, I will share the. Please message me once in WhatsApp. I will
Sure,
share.
sure, sure,
I will share
sure.
you the file, and
Okay.
yeah, you will see next week. I don't remember what is there actually. We just check once.
Hmm.
What topic is there in next week? Yeah, next, next week we have some this regarding testing. We will study about testing and the strength analysis of reinforced soil. So, okay, that is also a very conceptual thing. We will see that there this more column and all this whatever more circle concepts and all these shear strength concepts, whatever we revised today, those things, all those things are derived from that only. So we will see that next week. So in today's there were no problem. Everything was theoretical only mainly. So in the next week we will solve some problems regarding that, and then we will be seeing the testing of geosynthetics.
Okay. Thank you.
Okay, okay. Thank you, sir. Thank you. Will I will just message me once. I will send share
Sure,
you.
sure, sure.
Okay, okay. Thank you.